Hi everybody, I'm Oscar. Today I'm going to be presenting my superhero logo for the final project of AP Calculus BC. We're going to start by looking at the index of how I'm going to be presenting this project to you. We're going to begin by looking at cross sections, what they are, what they mean, and if you haven't looked at them, we're going to briefly go over what they are so that you understand the context of this project. Afterwards, we're going to go over a description of the work that I did. This means building the logo, looking at region 1 and looking at region 2. When we're done with that, we're going to go over an explanation of the work that I did for the experimental and theoretical volumes. Afterwards, we're going to compare the two of them and see how I did in that area. Then we're going to go over how the models were built and look at possible changes that I should make if I were to take on this project one more time. Then we're going to go over the purpose of the project and what it was meant to be for us students, finally ending the presentation with the meaning of the Green Lantern logo to me. Now I'm going to go over the cross sections and I'm going to present to you what they are. For example, take a look at this shape. It's a cylinder. Imagine that it's full for the purpose of this project, but what it is a 3D shape that with a cross section, what we're essentially doing is cutting it in any direction and then finding the shape that is left afterwards. For example, imagine if I cut this cylinder in half, I'm going to get another smaller cylinder, and if I were to look through it, I would see a perfectly round circle because that's the shape that's left if I were to cut it at that angle. And if I were to cut it in another direction, say diagonally, I would be left with this shape. You can see that from the front, it looks like a circle, but once you start turning it, you see that it's another shape that's filling this area, and that's why cross sections can be so versatile, because you can cut it from any angle and you're going to get a different shape. Now we're going to move on to the Desmos, and this is what my logo looks like built inside. We're going to go briefly over explaining what I did. I started by building the box outside of the ring of the lantern by doing simple squares, simple lines. Afterwards, I did the circle surrounding the lantern, which is modeled by the function x squared plus y squared equals 21.5. I found that area to work perfectly with the logo. Then I decided to take on the edges of the lantern, finally ending it with the center. You can see that by the end, I have the two curves surrounding the lantern and the middle part. This is not really important, but now we're going to go over region 1 and region 2. The region 1 that I was assigned, which is parallel to the x-axis, is this upper right corner around the first circle and in between the final box. This was supposed to be done with semicircles as cross sections. Afterwards, the second region that you can see on the right is just the curve of the lantern, and it has to be parallel to the y-axis, and I had to do squares for this cross section. Now we're going to go ahead and explain the math that I did for the experimental part of the cross sections. This is for the semicircles. It was half a circle pasted on top of the physical graph. First, what I did was that I measured the diameter that I was going to have. I cut it in half, and then I found the area of that, multiplying by pi and using the radius as r. Then I squared that, and afterwards what you had to do was find the volume. So I went ahead and used the actual height of the carton, which was 0.4 centimeters, and I got the volume. Then once we added that, we got 108.59 centimeters cubed, but since we had to divide that down to the units that we used, which in my case were 2.35 for the semicircles, I got that the volume was going to be around 8.37-ish cubic centimeters. This is the presentation of my actual work for the theoretical value. So what I decided to do in the beginning was use the formula that is presented to you on the screen. And you can see that in the work I began by looking at 5 squared, because if you take a look at the square inside the region, you can actually work out that x squared equals to 25 is a better square to look at when presenting this. Afterwards, I took a look at, since there's a small region, there's a small space where you can you have to work with it. You have to then add it to the circle that we're representing in the center. You can see this is the circle that I'm talking about, and this is a small space that we're talking about when it comes to the square. The square fits in well with x squared equals 25. So when presenting the final the final volume that we got that it was 8.87 cubic centimeters, which is a little bit different from the value that we got by doing the actual work. Now we're going to go ahead and move into the squares. This one was a little bit longer, which is why I needed two different spaces. I used more cross sections, obviously, which means that it was technically going to be more accurate, but we're going to discuss that later. I did the same thing, but since it was a square, instead of doing the pi r squared formula, we're going to use the squared formula, which is the dimension squared. We took the area first, and then we multiplied it by the depth, which was again 0.4 centimeters, giving us a volume total of 357.85 cubic centimeters, and when divided by the units, it would be 11.45 cubic centimeters. So we're going to continue by defining what the actual or the theoretical volume of the shape is going to be if we were to use squares as cross sections for the second region. We're going to start by defining that the radius is going to be depending on the height of both figures. So what we're going to do is that we're going to create an integral and then subtract the height of the circles to find the radius and then calculate the volume. So we limit our integral from negative 1.575 to positive 1.575, since that's where the function of the small circles cover, because if we go past this using this sort of equations, it's going to be impossible to calculate it. So instead, we use an integral from 1.575 to 2.31, and then this is going to be the volume that is going to be depending on the function of the outer circle, and therefore we use this equation. Since the area of both sides is going to be equal on positive and the negative side, we're going to multiply what we get times 2 to get the volume. This being because it's symmetrical and it's reflected on the x-axis, so we can do that to find the actual volume. Now we're going to go over the margin of error for region 1 using this formula of volume of experimental minus the volume of theoretical over the volume of theoretical. And I found that the region 1 margin of error is going to be 5.6%, which is pretty good. However, the margin of error for region 2 is going to be much smaller, and it's going to be not much smaller, sorry, it's going to be a little bit smaller. But when we're doing these projects, I feel like it's something to be proud of. Now we're going to go over what I did to build these models. First, we're going to start by the region 1 model. Since it was going to be in semicircles, what I decided to do was that I took my cardboard and with a ruler, I drew what the radius was going to be, multiplied it times 2, did an arc, and then I proceeded to cut it out in pieces and organize them so that I wouldn't lose the order. And eventually I got to the big ones, which were easier to do than the smaller ones. As for the second region, what I decided to do was that I took a cardboard and with one edge I worked out what the area was going to be after measuring, of course, with the paper, the length that each side was going to be needing to take. And since they were squares, I could just use the same length on both sides. And when I was done with that, I could cut them out for the cardboard and paste them one next to each other on top of the paper to show essentially what the volume is going to be. Some possible mistakes that I made during this project and that I should probably take into consideration if I were to do this again, or that I would probably try to use smaller cross sections, because I feel like doing 0.4 as the width or the height of the carton, whichever you want to use, it took a little bit more time to calculate, a little less time to calculate, but it was going to be more accurate if I decided to do a smaller section, because if you take a smaller cross section, it means that you're narrowing it down further down, and it's going to show more accurate representation of the value is going to be. So the actual calculation might have been longer, but it would have been for a more accurate value. Then I feel like I should have also used the geometric compass to measure the semicircle, which was a big mistake that I did for this part. And I should also have used a better tool to cut, maybe something more precise, because as you can see in some of the squares, there were some rough edges, and that doesn't matter, but for presentation, it's pretty important. And in general, I feel like I could do better in my integral practice. I feel like that part was a little bit difficult to do. And especially with the organization, sometimes I feel like maybe I might have lost one of, or not, I'm not really sure, but this is a problem that it creates. I'm not sure if I maybe made a mistake when it comes to organizing myself for the contents of the cross sections. Now, the purpose of this project, I feel like, was to show us what we've seen it in 2D, but now that we're doing it in 3D, it gives us a better understanding of what cross sections are, what volume is, and how we do what we do, and what it means to do it on another level. So I feel like this was a pretty interesting project for us to understand the concept of not only cross sections but integrals and, in general, geometry implemented into the calc lessons. And finally, the reason that I decided to do the Green Lantern logo was because I really like the superhero. Ever since I was a small kid, I was a pretty big fan. I used to have this dish with the entire Justice League on it. So the reason that I decided to do the Green Lantern one was because I was a pretty big fan of that. Plus, if you don't know, Green Lantern represents power of will, which is something that I really could use. So I decided to do that for this project because I found myself that throughout the year I could have done better and done a better job if I had presented a little bit more will, which is something that I'm going to consider for my future. So that was my project. I hope you liked the presentation. I hope you liked the project. And I hope I did well. And yeah, see you. Um, sorry. Bye.